Hey everybody, welcome back to chemistry. And so we're continuing on through chapter 8. So what we're going to do is we're going to study the structure of the atom, and we're going to try to understand especially the motions and positions of electrons around atoms. And so the early experiments that determined this information about electrons were done by looking at the interaction of light with atoms. And so before we talk about those kinds of experiments, what we need to do is talk a little bit about light. So let me just kind of go back in time a little bit. And so let's pretend that it's about 1900. So in 1900, which was, I guess, over 100 years ago, we really thought the universe was sort of broken up into two general realms. There was the realm of matter, and then there was the realm of light. So the realm of matter was the idea that all matter is comprised of particles, or atoms, if you will. And that all matter, because it's comprised of particles and atoms, all matter, because particles and atoms have mass, all matter also has mass. And so if matter has mass, then it is going to be described by the classical laws of motion, which were created by Isaac Newton in about 1665. Now, on the other hand, there was the realm of light. We thought light, on the other hand, in 1900 was not made of particles. Instead, light was made of massless waves that traveled through space. These massless waves were called electromagnetic radiation. And we need to understand sort of the properties of electromagnetic radiation. But before we get to that, what I want to do is talk about waves in general, and then I'll talk about light waves in particular. So first, let's talk about, in general, what waves are. What a wave is a vibrating disturbance by which energy is transmitted through space. So to get a sense of what that's about, let's just imagine, for example, a water wave. So pretend you're on the beach of a lake, and let's say out from your position in the water you see, say, a large cork in the water, or say a water buoy in the lake. And then at the same time, beyond that, you see a slow-moving boat approach, and it'll go by, and so what happens? And so one of the things you'll probably notice is as that boat goes by, it is going to create waves in the water. And so the waves of the water are moving forward toward you. And what will happen is the waves in the water will pass by the cork. The cork will start moving up and down as the waves pass by. And so the waves will continue on to the beach. And then maybe if the waves are strong enough, what will happen is the waves will knock down perhaps a small sandcastle that you built on the beach. So that should tell you one thing that's important about waves, is that water waves, and pretty much all kinds of waves, are very good about transferring energy. And so originally the energy came from the motion of the boat, and the waves just transferred that energy out from the boat to the beach, and you see that energy was able to sort of knock down the sandcastle. One of the things we'll sort of see and understand about the cork is that it can be used to sort of understand the wave's properties. So let's say the waves pass the cork, and the cork moves up and down, up and down, up and down. Now, if we look particularly at the motion of the cork, it starts, say, at a high displacement in the water, say up, and then it falls, and it continues to fall to get to its lowest displacement in the water, which you can call down, and then it goes back up again. So that movement of the cork from its highest displacement to its lowest displacement back up to its highest displacement again is called the cycle that the cork is undergoing. And so the number of times that cork undergoes a cycle per second is the frequency of the cork. So if the cork is moving up and down and up again, and it does that 2 times in a second, then you would say the frequency of that cork is 2 per second. Or, for example, maybe you have another wave that passes by, and then maybe the wave is moving faster, and so the cork goes through more cycles in a second. Maybe it's 10 per second, for example. And so you can see that different waves will have different frequencies. Another kind of property of waves that you sort of need to understand is the distance between the midpoint of the wave and either the crest or the trough is called the amplitude. Some other properties of the water wave we're sort of thinking about here is that we can think of the speed of the water wave is simply maybe the distance that, say, a crest travels over a certain amount of time. And also, you'll probably notice with this water wave that's heading toward you is that there are many crests that are appearing and they're heading toward you. The distance between the crests will probably stay constant as they're moving toward you, but that distance between the crests is considered to be the wavelength of the wave. So to give you a sense that waves can have different properties, now imagine that another boat goes by, and let's say this is a high-speed motorboat that's passing you by. If that's going to go by, then what you can maybe imagine is going to create a new wave that is moving faster through the water. And so if it's moving faster through the water, then it hits the cork, so the crests are hitting the cork faster, and so the cork is going through its cycles much, much, much faster. So maybe instead, in the original wave, it was 2 cycles per second. Now maybe the cork is going up, down, up again, not 2 per second, but maybe it's now doing at 10 per second. And so what you would say for this wave is that the frequency is much faster. So the point I kind of want you to see here is that waves can have different properties. They can have different frequencies, they can have different speeds, and they can also have different wavelengths. Now, you can describe light, which is a form of electromagnetic radiation, using waves. And the properties that we define for water waves, which are frequency, wavelength, amplitude, and velocity, we can also apply to light waves. And so we're going to go ahead and do that now. A thing to keep in mind is that light waves do not need matter to pass through in order to propagate and transfer energy. Instead, as you probably know, is that light waves can pass through a vacuum. So one of the questions you might have is, if light waves are able to pass through a vacuum, then what are the things that are kind of moving back and forth to allow that light wave to pass through in a vacuum? So with water waves, it was the water moving back and forth that was creating the wave motion, and that was creating the energy that could allow the water wave to propagate forward. But here, we don't have water molecules with a light wave. The light wave is passing through a vacuum when there are no molecules at all. So the question is, what is waving in a light wave? What is moving back and forth in a light wave? And instead of having molecules in a light wave that are moving back and forth, what you have instead is an electric field that is moving back and forth. And so there's a picture of it there on that screen. And so what you can see is, if you look at the red line, that is a sinusoidal shaped curve. That's what is described in math. And that describes light wave moving in space. And so it's going up and then down and up and down and up again as it goes through forward in space. Think about that as a varying electric field. So what is an electric field? So electric field is where, for example, let's say you have a positive charge. And let's say not too far away from it, you have a negative charge that is nearby. Positive charge is going to feel a force toward the negative charge. And so any space around the positive charge where, say, a negative charge will feel a force is the electric field of that positive charge. So in this diagram, we can sort of imagine where the electric field, as it's passing by, you can see it's waving there in the picture, where it's going to be strong versus where it's going to be non-existent. So let me explain that. So let's say you're at this point here of the light wave. And so what you can see is the red line is the electric field component. The distance between the red line and the point in space is pretty great. And so that might indicate at that particular point of space, the electric field is pretty strong. So if you had, for example, a negative charge here at this point, let me just draw a little negative sign with a circle around it, a negative charge there at that point, it would feel a relatively strong force from the electric field. But if the negative charge were a little bit further along here, where the wave seems to be at the x-axis at 0, then it's not going to feel any force at all from the electric field. But if it's a little bit further around down here, you can see that the electric field is again strong but going in the opposite direction. And that negative charge will feel a strong force as it did before, but in the opposite direction. So all that a light wave really is just undulations of an electric field as it's passing through space. And so at one particular point, if there was a charge there, it would feel a strong electric field, and then nanoseconds later it would feel no electric field, and then nanoseconds later after that it would feel another strong electric field, and so on. Also, at the same time, when this electric field is sort of propagating forward through space, you have a magnetic field which is oriented perpendicular to the electric field. So you can see that in the picture there, that the electric field is drawn as a red line and the magnetic field is drawn as a green line. And so you can see that the magnetic field is sort of perpendicular to the electric field. And that just indicates that not only is there a undulating electric field that's moving forward in space, but there's also an undulating magnetic field. And so if you had some kind of, say, magnetized particle in those positions that I showed before instead of the charged particle, it would feel parallel strengths from the magnetic field as I sort of described from the electric field. So even though we have a light wave that is just an undulating electric field and a magnetic field propagating through space, that light wave can be described using the properties that we use to describe water waves. So we can describe a wavelength for that light wave, a frequency for that light wave, and an amplitude for that light wave. And so if you imagine a white wave moving through space, and there are places in space where the electric field is strong, you can think of those as the crests of the light wave. The distance between the crests of the light wave is also called the wavelength. And that wavelength is symbolized by the Greek letter lambda there. The distance that the peak of the crest has versus its midpoint displacement, that distance is the amplitude. And notice that the distance to the peak of the wave is the same as the distance to the trough of the wave. So another way to characterize a wave is through the frequency of the wave. So we can sort of define the frequency of a wave in a couple of ways. And so one way is just measuring the number of crests that pass a certain point per second. The units that we use to describe the frequency of a wave are hertz. And so hertz, again, is just the number of cycles, in other words, crest to trough to crest, that pass a certain point in space per second. So another sort of an example of that is, let's think of, like, for example, a washing machine in the spin cycle. And so you know that in a washing machine, there is a rotor inside the washing machine which is spinning pretty quickly. And so let's say it does a complete spin. It does one complete cycle very rapidly. Let's say it does, say, maybe 20 cycles, a complete spin in 1 second. So the way you would describe the frequency of that rotor in the washing machine is that it does 20 cycles per second. Another way you could say it is it's 20 per second, or if you have cycles per second, the units to describe that is something called a hertz. And so what you can say is that that rotor is at a frequency of 20 hertz. Another formula which is kind of important to know is the relationship between speed of a wave, its wavelength, and its frequency. And so I have that formula there. Speed is equal to the wavelength times the frequency. So speed is symbolized by the letter v. Wavelength is symbolized by the Greek letter lambda. Frequency also has its unique symbol, which is the Greek letter nu. And the Greek letter nu looks like sort of a weird looking V there. The units that you usually associate with these variables for velocity in terms of a light wave, it's going to usually be meters per second. For wavelength, it's usually going to be meters because, again, velocity is going to be meters per second. And so you'll have to probably convert wavelength of any sort into meters. And then for frequency, that weird V there, that nu, that should be in cycles per second or in hertz. What you're going to see is that light waves can come in a lot of different wavelengths and frequencies. But one thing that is true for all light waves, no matter what its wavelength is or its frequency, they all travel at exactly the same speed in a vacuum. And that speed is 3.0 times 10 to the 8 meters per second. That's a number that you'll probably need to know for your test. I don't think you'll have to memorize that. That will probably be on the sheet of constants that will be given to you for the test. Okay, another thing you should know is that when we're considering visible light, and so I think you know what visible light is. Visible light is light like you get from the sun or from a light bulb or something like that. You probably know that visible light, if sent through a prism, can be separated into its individual colors: red, orange, yellow, green, blue, indigo, and violet. So each of those colors of visible light will have light waves of a different wavelength and a different frequency, although they'll all be going at the same speed, which is 3.00 times 10 to the 8 meters per second. Now, one thing to keep in mind is that this visible light is only a very small portion of all the possible light waves that exist. All the possible light waves that exist is called the electromagnetic spectrum. What I've kind of showing you here in the top picture is the broad range of wavelengths you can have for the individual light in the spectrum. So at the very left end of that picture, what you can see is you can have wavelengths that are pretty long. In other words, there's a pretty good distance between the crests of the wave. If you have waves where you're looking at, say, the distance between the crests of the waves are greater than a centimeter, so it could be like 10 centimeters between the crests of the wave, or a meter, or 100 meters, those kinds of electromagnetic waves are radio waves. And the thing to keep in mind is that your eyes cannot detect waves with such a huge wavelength, and so these are completely invisible. So you get radio waves going to your radio all the time, and you probably know that, well, you can't see them, right? And so the reason is the radio waves are so long in length that we don't really have the receptors in our eyes to receive them, to know that they're there. Now, what we can do is we can shorten the wavelength more as we go to the right in that diagram. And so when you get the waves where the wavelength is less than a centimeter and you're getting into 0.01 centimeters, maybe you're getting into micrometers, nanometers, you're getting into the infrared portions of the spectrum. And then from about, say, 750 nanometers down to about 380 nanometers, that is the distance between the crests of the waves that you can see as visible light. Now, the waves that can be produced in the electromagnetic spectrum can have wavelengths that are shorter than 380 nanometers. They can go down from there to, say, 300 nanometers to 200 nanometers to 10 nanometers. That region of the electromagnetic spectrum with wavelengths, say, below 380 nanometers and going down to 10 nanometers is the ultraviolet region. And then after the ultraviolet region, you have shorter waves being X-rays, and waves even shorter than that being gamma rays. And again, sort of the key thing to sort of remember here is we have a very broad range of wavelengths that electromagnetic radiation can be. So visible light is only a small portion of that. But given that there's a broad range of wavelengths and therefore a broad range of frequency of these waves, but all of them will have the same speed in a vacuum, which is 3.0 times 10 to the 8 meters per second. So here's sort of another description of the electromagnetic spectrum. And so again, as we're going from left to right, we're starting out with very broad waves. In other words, there's a great distance between the crests, and as you go to the right, that distance between the crests gets shorter and shorter and shorter, and then you go through the visible part of the spectrum, and then from there you go shorter and shorter and shorter down to the gamma rays, which have an extremely short distance between the crests. It's going to be like in 10 to the negative 15 meters range, so it's a very short distance. Now, there are a couple of things that you sort of need to know about this diagram. So one of the things you need to know is you need to know the order of colors that occurs when you go from highest wavelength down to the lowest wavelength. And so we have that sort of blown up there on the bottom portion of that picture. And so what you can see is when you get to waves where the distance between the crests is below 1,000 nanometers, you still can't see them. But when the distance between the crests lessens to, say, 750 nanometers, then you can start seeing them sort of as a very dark red color. And then if you were to get waves of smaller distances between the crests, they go down to red color and then orange and yellow. And by the time you get to a distance between the crests of about 500 nanometers, you're starting to get into the region between green and blue. And this can continue, and then you go to indigo, and at the very far end at 400 nanometers or 380 nanometers distance between the crests, then you're getting into the violet. So you need to know the order of colors that appear as you go from great wavelengths on the left to lesser wavelengths on the right. That order is red, orange, yellow, green, blue, indigo, violet. And so you can sort of remember that with the acronym ROY-G-BIV. So each of those letters represents the color. So that's one thing you've got to know. Another thing to know is as you're going from left to right, you're decreasing the wavelength of the wave. Let's think about what's going to happen to the frequency of the wave. So keep in mind that with all these waves from left to right, they're going at the same speed. They're going at the speed of light, which is 3.0 times 10 to the 8 meters per second. So imagine a long wave passing a point in space. It's going to take some time for those crests to pass that point. So the frequency, the amount of time needed for the crest to pass a certain point is going to be relatively low. But if you're dealing with small waves, like say gamma rays, they have tiny wavelengths. The crests are very close to one another, and they're going the same speed as the longer wavelengths. Then the tiny waves, you're going to get a lot of crests past a certain point every second. And so what that means is that the frequency of the wave is going to be much higher. So as you go from left to right in that graph, although the wavelength of the waves is decreasing, the frequency of the waves is increasing. Okay, another thing you'll learn later, which is more important later, is that as you go from left to right, the energy of the wave increases. So waves on the left side of that picture there, like radio waves, they have relatively low energy associated with them. But waves on the right side of the picture, getting to X-rays and gamma rays, those are the ones with short wavelengths and very high frequencies. They will have more energy associated with each of the waves. And we'll talk a little bit more about that later. And again, this is just a reminder that all these waves that you see here, from radio all the way to gamma radiation, they all travel at the same speed, which is the speed of light, which is 3.00 times 10 to the 8 meters per second. Okay, this just kind of reinforces the idea that as you shorten the wavelength, the frequency of the light should increase. And so let's just kind of go through that here. So here I have sort of a picture of what waves that are red look like versus waves that are yellow versus waves that are blue. And you can see that the waves that are red have relatively long wavelengths. The waves that are yellow, the wavelength is a little shorter because the distance between the crests are shorter, and the blue waves, the distance between the crests is even shorter than that. Now imagine that those three waves are all traveling at the same speed, and they are. They're traveling all at the speed of light, which is 3.0 times 10 to the 8 meters per second. If they're all traveling at the same speed, imagine which of these waves will have the highest frequency. In other words, which of these waves will have the most crests passing a certain point every second. So you can imagine with the red waves, because the crests are further apart from one another, you're not going to have so many pass a certain point per second. And so there won't be many cycles per second that are passing by. But as you go from yellow to blue, because the wavelengths have shorter, then you'll have more crests that are passing a point every second. And so if that's the case, then the frequency of the yellow and the blue waves will be higher than the red, and the frequency of the blue waves will be the highest of all. So this is just to point out again that as you decrease the distance between the crests and you're decreasing the wavelength of the waves, assuming that the waves are all traveling at the same speed, that you're going to increase the frequency of the waves. In other words, the number of crests that will pass a point per second. So another thing to sort of keep in mind when you're seeing pictures of these waves, here on the right, where we have drawn two waves. They have exactly the same wavelength, and if they are going at the same speed, they will have exactly the same frequency, but you can sort of see that the waves are different from one another. And so one of the things you kind of might recognize is that the wave there in the center, the crest is not very high from the midpoint, and neither is the trough. And so the amplitude is not that great, but the wave below it, the crest is very high from the midpoint, and same with the trough, and so the amplitude is much greater. Now, with light waves, that corresponds to the intensity of the light. So if you have a relatively dim light, what that would imply with this wave theory is that the waves have relatively low amplitude. But if you take that dim light and you keep the wavelength the same and the frequency the same, and you just increase the brightness of the light, in theory, all you're really doing is you're just increasing the amplitudes of those waves. Okay, so another thing you sort of need to know about this is that you need to be aware that some of these wavelengths here are considered to be ionizing radiation. So one of the things that I kind of mentioned before is that, again, as you go from left to right in this picture, as you go from radio waves and then microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays, what is going on is that although the wavelengths are decreasing, the frequency of those waves is increasing. Also, the energy of the waves is increasing. So once you get to beyond the visible light, as you're going to the right, you're getting into the ultraviolet, X-ray, and gamma rays. Those waves have such a high frequency and have so much energy that if they are able to enter cells in your body, they can break up the bonds between the atoms and molecules, and the atoms will be released as either ions or free radicals. And because electromagnetic radiation at this area, the ultraviolet, X-ray, and gamma rays, can create ions from molecules, these waves, the ultraviolet, X-ray, and gamma rays, are called ionizing radiation. So here's sort of an example of the effect of ionizing radiation. And so when you get a sunburn, this is due to ultraviolet radiation. So you probably know if you wait time after you get a bad sunburn, the cells on your skin will die. And so the reason why that happens is because the ultraviolet radiation, when it got into the cells, it broke bonds between the atoms of molecules, and those atoms were released as ions or free radicals, and they're very reactive, and they will break other bonds between molecules, and so you'll have a lot of degradation of the molecules in the cell, which leads to the degradation of the cells on the whole, and the cells will die. Now, one thing that's kind of interesting, you might wonder, why is it your skin turns red when you get a bad sunburn? Well, one of the things that happens is that when your cells are dying, they're releasing proteins into the bloodstream called cytokines, and some of those cytokines are vasodilators, and they cause your blood vessels to dilate. The reason why it appears red is because after a bad sunburn, those cytokines are released, and they cause your blood vessels to open up and release more blood into the vessels, and so it appears more red. Another example of ionizing radiation that can be used in medicine is using X-rays or gamma rays, these very high frequency radiations with a lot of energy. They can be used to kill tumors. And so here we have sort of an example of how this could be used. This is a technique called gamma knife, where you put a patient into this device. This device has multiple sources of gamma radiation, and what you can do is focus beams of gamma radiation from different positions to meet onto cells that you want to kill off, say a tumor. And so because the gamma radiation is such high frequency, has such high energy, when those waves intersect from those different positions, they create tremendous amounts of energy which will ionize a lot of molecules very rapidly within those cells and should kill off the cells. And so, in fact, I think we have a place at this campus where you can have this gamma knife treatment done, and it's supposed to be at a small fraction of the cost of regular surgery. So with the next presentation, what we're going to be doing is we're going to be solving some problems related to electromagnetic radiation. So thank you for listening, and we'll see you next time.